Okay. Now, when you graph the ionization energies, you're going to see a graph that looks like, I don't know, something from an EKG, something from a heart monitor. You're going to see peaks, sharp valleys. It's going to look like the graph of Wall Street, okay? So the way you do it is, you're going to put the atomic number here. You're going to start at 0, okay? And you're going to graph it. Now, those numbers, those ionization energy numbers, are that comma there is point. That's a decimal point. It's not thousands or hundred thousands. It's those are decimal points. Those commas. Okay, so you want to graph it. If you're lucky enough to say, okay, you know, this can be one whole unit. You're only going to be able to graph it to the tenths place at the most. For instance, that would be 0.5, 0.6, 0.7, 0.8, 0.9, and then 10, yeah? So you're not going to be able to graph it perfectly. But you're going to be doing so much data, you're going to go up to 103. Clear? You're going to go up to 103. And you're going to the data will come out. I think somebody has their, are you done or you're part of the way done? You're done? All right, I'm going to show you a graph. Thank you. Oh, this is pretty cool. Okay, you can see this graph here. Can you see this on that monitor? Can you see that? Yes? Can you see that?
You have to back up a bit.
Back up? Can you actually see it?
Yeah. Move it up a bit.
Move it up a bit? Is that good?
Yeah.
Can you see it? Can you see it? Does it make sense? All right. TJ, what do we got? Does it look good?
Yeah, you can see.
Good, okay. You see that? That's pretty good. It's actually pretty good. I'll help you. You got to attach it a little bit better.
Oh, yeah.
I'll work on that with you. Okay, that's not a problem. That's a very good graph. Okay, so I just want to try to interpret some of this data briefly. I want to talk about how you get these values. Okay. Now we know that here is we'll look at period 3. All right. Let me draw period 3. Can I see over here? Yeah, we got to look at this now. How's this look? Let's do it in black so you can see it. Okay. Okay. We're going to go 1, 2, 3, 4. All right. So this is going to be period 3. So this is going to be sodium. And then what's next? What's after sodium going up? Sodium, then what? What is it? Magnesium? All right, is anybody here today? It would be very helpful, and I can get so much more done if you actually participated. The periodic table is right there. So you can obviously see what's next. What's after magnesium? Aluminum. Then what? What is it? Silicon. And then what? Phosphorus. Then what? Sulfur. And then? Chlorine. Oh, we have to do one more. Sorry, I thought we did them all. And then what's at the end? Argon. Notice I drew the P slightly above the S. Okay? It's a higher energy level, correct, okay? So what's the electron configuration for sodium? It's just this, right? Right? It's just 3s1, correct? Yeah? So that's the electron that I'm taking away, all right? That's magnesium. That's aluminum, yes? That is silicon, yes? Are we there? Okay. This is phosphorus. This is sulfur, am I correct?
You're missing.
Am I wrong? Silicon, phosphorus, am I wrong?
No, wait.
Wait, if it's P,
Is
is
it
there
three?
three circles?
Yeah.
What is it?
Three.
Circle.
Three.
P.
No,
Like,
the
it's
section.
in the P block.
The P block. You have four orbitals. You have four orbitals.
Three orbitals.
Yeah.
3s1, 3s2, 3p3.
okay.
Okay, are you okay? Am I okay? Go ahead. Think about it. Am I off camera?
Yeah.
All right. Think about it. Yeah. Am I? Is it okay? You got to understand this. Isn't it three? Look at it. Look at the periodic table. Isn't it 3p3 phosphorus? Right. And then sulfur is what? 3p4. Right. Right. Yes or no? Yes? And then what? Chlorine. All right. Kind of rushing this. That's chlorine, is that correct? Yes? And then argon. Yes? Now, so what's going to be the easiest element? What's going to have the lowest ionization energy of any element? What element? What element's going to have the lowest ionization energy? Sodium. This is the one right here. I'll put a little dot at the head of the arrow. That's the electron you're removing. Now, think about what's left over. Right? Kind of drew that in weird. I'm a little dyslexic, my apologies. It's hard to, whatever. So that's going to be 2. This is 2s, this is 2p, correct? So if it loses that electron, the sodium, it's going to have a very stable configuration. Do you see why elements react? They don't react. Octet rule, I'm so sorry that anybody ever said the octet rule. It's for people who have no intelligence. The octet rule. It's not the octet rule. They want to be just like the noble gas. Yes, okay, the noble gases have 8 electrons in the valence shell, but the most important reason, Michael, is the fact that they want to be like the noble gas. Okay, fine. After the fact, you can count the electrons all you want, but the overriding reason is it wants to be like a noble gas. That's what happens in nature. Does sodium go around counting how many electrons that element has that it wants to bond with? No, it automatically wants to be like an element. It wants to have 11 protons. It wants to be like itself. It doesn't want an identity change. It wants to still be sodium, but it wants to pretend that it's a noble gas. Can it do that? Do you ever pretend? Do you ever put a face on where you're pretending? I do all the time. I pretend I like him. Kidding. You pretend all the time, so they're just pretending. That's all they're doing. They want to be like a noble gas. They want to be happy. They think the noble gases are happy. Look at Mr. Holland down there. Just simply call him Mr. Noble Gas. Look how happy he is. He's so happy. He's so happy. He met a noble gas and is very happy. He is now a noble gas. Clear? You understand? He's not really a noble gas, but we're going to humor him and say, hello, Mr. Noble Gas. Excellent. You get it? That's why they do this. So that's going to have a very low ionization energy, true or false? Okay? Will magnesium have a higher ionization energy? Yeah, because, yes, it does. It does because it has a full S subshell, so it's bound to another electron. You're not just removing an electron. It's bound to another electron. Electronically. It has an opposite spin. They're attracted. So it's going to go up. Isn't it? It's going to be higher. Now look at this one. Harder or easier? Remember, we're comparing it to the immediate former. What does that mean? The one that came before, right? The one that came just before. So do you think aluminum ionization energy will be higher or lower? Will it continue to go up? It's going to be lower, and I'm going to tell you why. It's going to be just a pinch lower because if you get rid of it, you have to understand, you have to be the element. Okay? We should get t-shirts made. Be the element. Ionization energy, comma. Ionization energy, colon. Be the element. Okay? You want to see what's happening, so if I get rid of that, I have a fairly stable situation, don't I? So now look at silicon. Silicon, hey, it's almost there. It's 2/3 of the way to a half-filled sublevel. So it's going to go higher now to get rid of it. So you're going to go higher. Okay? It's going to get higher. Now, let's look at the next one. Phosphorus. Look at that one. You're going to get a big boost. It doesn't want to get rid of it. A half-filled shell, what's the only thing greater than a half-filled shell? What's the only thing more stable than a half-filled shell? A full shell. Half-filled shells are pretty cool. You play poker and you get a half-filled shell, you can beat everybody. You ever play poker and get a half-filled shell? Andrew? You weren't listening to me?
No, I was. I just didn't understand it.
Well, good. That's a good thing because I'm being silly. Andrew's like stunned. He just has no idea what I'm talking about. Playing poker, having a half-filled shell. I know what a full house is. I don't know what a half-filled shell is. Were you confused a little bit? You thought I was being serious, didn't you? You weren't sure.
Yeah.
You had that little.
I was unsure.
There was a little, just a tiny bit of. Is he trying? What is he saying? Okay, I understand. Yeah, I'm being silly. Okay, so the half-filled shell. Where am I? Did I put the half-filled shell in? No. You're gonna get a big boost here. Big boost, right? Now you tell me, sulfur. You're gonna get a drop or not? You're gonna get a drop or not? You're gonna get a drop or not? Sulfur. Sulfur is this one here. It's gonna go up. Look what happens if I get rid of it. If I get rid of it, what do I have? Okay, I know it's bound to something in a p orbital. I understand that, but be the element. If I get rid of that electron, what is the configuration? It's going to be 3p3, isn't it? Isn't 3p3 mucho stable? Remember, Andrew, you play poker and you get a half-filled shell, man. You can beat everything except for a full shell, right? Remember that. Next time you play poker, remember that, okay? Just don't tell anybody, because they'll think you're very weird, okay? Plus you are sitting, is that the Miley Cyrus haircut too? Or? Uh-oh, I said that on film, my apologies. I know, I know. It looks good. You're very, very conservative. You look like fine Republicans. I like that. Okay, excellent. Now. See where you started? See where you started, Russian? Okay, now. All right, now. So, you're going to get a jump. Did I put the big jump in? Yeah, I did. Now, you're going to remove the sulfur. Where am I? Yeah, the sulfur one. You're going to get a decrease, aren't you? It's going to be kind of a big decrease, isn't it? You will, because you have a half-filled shell left over. Now we're going to go to chlorine. Does it want to get rid of that electron? Absolutely, positively, up or down, black or white, left or right, anywhere a squirrel can go, no. It does not want to get rid of that electron, man. It wants to hold on to electron. That chlorine is saying, no, don't touch my electron. Okay, it is. It's saying that. I heard it. Every time I walk by chlorine, I hear that. It's like, no, don't take it. And what happens is, because it's very near what? If it gets one more electron, it's going to have a valence shell of what? Excuse me?
Of a noble gas.
Thank you, Andrew. Of a noble gas. I like that. That's Andrew's radio voice. Of a noble gas. Okay, excellent. All right, so it's going to be higher, much higher. And then what about the noble gas? What about neon? Or argon? That's argon. Argon. That last electron. Can I pull this down a little bit? That electron right there. Is that going to be mucho difficult to get over, to get out of? What do we think? Yeah, it is. That's going to be up. So you get something that looks like this. Does that look like what you got?
Yep.
And then it's simply going to repeat. It's going to repeat. Now, this is the third. This is 3. This is period 3. You're going to have period 2 on the left of it, aren't you? Yes? Now, what's the difference between 2 and 3? None, really. What's the only difference you're going to have?
The maximum is
It's going to be shifted up or down.
down.
It's going to be shifted down. In other words, it's going to look like this, right? Right? It's going to look like that, right? But the other one is going to be like this. It's going to shift down. Why is it going to shift down? Why is it going to shift down? I'm going to stop. I'm going to stop for a minute, okay? And I'm going to go over the periodic table. I'll reset up. And we'll talk about ionization energies and how they change. But do you understand this? This is really important. Do you understand now why we might have done electron configuration, Aufbau rule, short form electron configuration, NLX? Do you see that now, Professor Malik? Excellent. I thought you would. Excellent. You get it? Are you with me? Okay, excellent. All right. Jacques, are you through walking around and inspecting the room? Excellent. Excellent. Just asking. Okay. End of video, ionization energy, part 1. Okay.